we're going to continue with 9.2. Luckily, a lot of these problems are pretty algebra based. So we talked about using different operations, right? Adding, subtracting. Then we did scalar multiplication. But in 9.2, we kind of do this multiplication of two vectors, not a scalar with a vector. A scalar makes a vector longer, shorter, changes direction. But the dot product is doing something a little different, right? There's geometry that's going on behind these, right? In the previous section, we showed geometrically what did it look like for two vectors to be adding together, right? Where you take the initial, put it on a terminal, then you go from initial all the way to terminal, and then that's what's happening on the graph. Scalar was making either larger, bigger, changing their direction. Now, what is a dot product doing? Now, the dot product is actually finding the angle that is created by both of these two vectors that are in question. Now, before we get into finding the angle that's created, we're actually going to see a different version of the dot product that finds it's a necessary part that we'll need to help us find the angle. And you can see a little bit already how I have this cosine set up here. But this first version of the dot product is very algebraic. It almost feels like a distributive property because we're going to take vector u and vector v, and the dot product, so it's denoted here with this dot, tells us that we are going to, the same way we added the corresponding components together, with a dot product tells us to multiply the corresponding components together. So a sub 1 with b sub 1, and then a sub 2 with b sub 2. So not too bad there. But one slight difference is that we're going to find the sum of that product. Right? This is where it's a little different. This version of the dot product gives us a scale, just gives us a number that we're going to use to find our angle in a little bit. But let's just practice this version of the dot product. So this version of the dot product tells us that we have to take the x components, multiply them together. So that's going to look like 3 times 4 plus negative 2 times 5. Right? Just multiply the corresponding components and add them together. And that will be negative 6. 3 times 4 is 12. Minus 2 times 5 is 10, which will leave us with the number 2. And if you want to try, pause the video and try the next example, you can. But this next example, I'm just using the I and J notation versus the inequality symbol notation. But same thing. The x component for vector A is 2. For vector B, it's 5. Plus, now, when you just see J, we assume that the scalar is just 1. And then we have negative 6. 2 times 5 is 10. Minus 1 times negative 6 is negative 6. And that's going to give us 4. Now we need to know how to do this version of the dot product because this is what's going to help us find what we're going to look at next, and that is the angle between the two non-zero vectors. Now, this saying a non-zero vector is just implying that the vector has some length to it. Because if it's a zero vector, it means it has no length, right? It's like the number 0. So it's just kind of a disclaimer. So dealing with now finding the dot product, this is the version that deals with talking about the angle between the vectors, right? That's what this dot product does. But for me to directly find the angle between them, well, I have to isolate this theta. And the only way to get an argument, a variable out of an argument, is that we need to use inverses. So if you notice here, so that's just what if theta is the angle between the two vectors, then the dot product is given by this formula. So again, two different versions. This is the second version, but this version helps us actually find that angle that's between them. So we start by first isolating cosine, which just means divide by the magnitude of u and v on both sides of this equation. And that isolates cosine theta with u dot v over the magnitude of u times the magnitude of v. Now this is why we also need to have the separate version of the dot product. Because if I try using this version of the dot product right now in the equation, I would replace u dot v with what we have here on the right hand side. And if that went in here, well, that would actually take me backwards, or it would just, the magnitude will simplify, and then I'll be left with saying cosine is equal to cosine. That's not going to take me anywhere. I need to have a separate equation that's going to help me finish this problem to find my angle. Now, like I always said, how do we get the variable out of the argument? Well, this doesn't mean multiplication, right? So the only way to get rid of the function is to use its inverse. So we will literally just take the inverse of this value of the dot product divided by the magnitude, the product of the magnitudes of each vector. Now we can sketch the vectors and try to have a rough idea, but for the sake of time, we're just going to get into actually doing the example. Now if you notice, I'm using both notations. I'm using the I and J and this inequality notation. Now we have the formula here. So to find my theta, I need to do cosine inverse of u dotted with v over u and v. So first, I'm going to use that first version of the dot product. I don't want to use this version because it wouldn't lead me anywhere. So this tells us it's going to be 3 times 5 plus negative 2 times, so you have to be careful. If you notice, I took the x component and multiplied it with the y component. When you go too fast, you can make these silly mistakes. So it's really 3 times 4 plus negative 2 times 5, which we already did this, and that gave us 2, right? It's just this example over here. 3 times 4, negative 2 times 5 leaves us with the dot product to equal 2. Now I have to find the magnitude of each vector. So the magnitude of u, well, we did that. Did we do that? No, that one's a little different. So the magnitude is the square root of 3 squared plus negative 2 squared which will give us the square root of 9 plus 4, which will give us 13. But I also need the magnitude of vector v, which is the square root of 4 squared plus 5 squared is equal to the square root of 16 plus 25. Let me move this a little over so I have a little more room. That's going to give me the square root of 41. So now let's take all this, right, and plug it in. So we're going to have theta is going to equal cosine inverse of, well, the dot product is 2. Then we'll do the square root of 13 times the square root of 41. And for the sake of time, I already have that. I have that calculation here. So plugging it into a calculator, make sure you do it correctly. You have to be careful with order of operations. But since we are looking for an angle, we're not looking for a radian. I put my equation in terms of degrees. And this is approximately 85 degrees. That is the angle between these two vectors. Now this next example is a little quicker, just because, well, 3 times 0 is 0. 0 times 2 is 0. So the dot product is 0. Now the magnitude of u is the square root of 9 squared plus 0 squared. It's going to give us 3. Magnitude of v is the square root of 0 squared plus 2 squared. And that's going to leave me with 2. Because it'll be the square root of 4, and the square root of 4 is 2. Now, the angle is doing cosine inverse of, well, my numerator is 0, divided by 3 times 2. But having 0 in the numerator is just going to give us cosine inverse of 0. Now you can use a calculator here, or you can remember that cosine is 0 at 90 degrees. Now, remember, when two angles or two lines make a 90-degree angle, we can say that those angles are or those vectors in this situation are perpendicular to each other. Another word for perpendicular, and you might hear, is that the two vectors are orthogonal to each other. It has to do with them being perpendicular. Now that's it for 9.2, just looking at the two different versions of the dot product. We are going to do in the next section, look at vectors in 3 dimensions. But this is truly going to be the same exact thing we did for 9.1 and 9.2. We're not going to change anything. All that we're going to add is that additional coordinate that's in question. Because we have the x, y, and now we'll have that z component. And for dot product, for scalar multiplication, for adding and subtracting, it's just that one extra term that we have to look out for. But we'll do that until the next video.